A fusion rocket is a theoretical design for a rocket driven by fusion power which could provide efficient and long-term acceleration in space without the need to carry a large fuel supply. The design relies on the development of fusion power technology beyond current capabilities, and the construction of rockets much larger and more complex than any current spacecraft. A smaller and lighter fusion reactor might be possible in the future when more sophisticated methods have been devised to control magnetic confinement and prevent plasma instabilities. Fusion power could provide a lighter and more compact alternative for spaceflight. The main advantage of fusion would be the very high specific impulse, and the main disadvantage the large mass of the reactor. However, a fusion rocket may produce less radiation than a fission rocket, reducing the mass needed for shielding. The surest way of building a fusion rocket with current technology is to use hydrogen bombs as proposed in Project Orion. But such a spacecraft would also be massive, and the Partial Nuclear Test Ban Treaty prohibits the use of nuclear bombs. Therefore, the use of nuclear bombs to propel rockets on Earth is problematic, but possible in space in theory. An alternate approach would be electrical propulsion with electric power generation via fusion power instead of direct thrust. Electricity generation versus direct thrust. Many spacecraft propulsion methods, such as ion thrusters, require an input of electric power to run but are highly efficient. In some cases, the maximum thrust is limited by the amount of power that can be generated. An electric generator that ran on fusion power could be installed purely to drive such a ship. One disadvantage is that conventional electricity production requires a low-temperature energy sink, which is difficult in a spacecraft. Direct conversion of the kinetic energy of the fusion products into electricity is in principle possible and would mitigate this problem. An attractive possibility is to simply direct the exhaust of fusion product out the back of the rocket to provide thrust without the intermediate production of electricity. This would be easier with some confinement schemes than with others. It is also more attractive for advanced fuels. Helium-3 propulsion is a proposed method of spacecraft propulsion that uses the fusion of helium-3 atoms as a power source. Helium-3, an isotope of helium with 2 protons and 1 neutron, could be fused with deuterium in a reactor. The resulting energy release could be used to expel propellant out the back of the spacecraft. Helium-3 is proposed as a power source for spacecraft mainly because of its abundance on the Moon. Currently, scientists estimate that there are 1 million tons of helium-3 present on the Moon, mainly due to solar wind colliding with the Moon's surface and depositing it, among other elements, into the soil. Only 20% of the power produced by the DT reaction could be used this way. The other 80% is released in the form of neutrons which, because they cannot be directed by magnetic fields or solid walls, would be very difficult to use for thrust. Helium-3 is also produced via beta decay of tritium, which in turn can be produced from deuterium, lithium, or boron. Even if a self-sustaining fusion reaction cannot be produced, it might be possible to use fusion to boost the efficiency of another propulsion system, such as a VASIMR engine. Confinement concept. To sustain a fusion reaction, the plasma must be confined. The most widely studied configuration for terrestrial fusion is the tokamak, a form of magnetic confinement fusion. Currently tokamaks weigh a great deal, so the thrust-to-weight ratio would seem unacceptable. NASA's Glenn Research Center has proposed a small aspect ratio spherical torus reactor for its Discovery 2 conceptual vehicle design. Discovery 2 could deliver a manned 172,000 kg payload to Jupiter in 118 days using 861 metric tons of hydrogen propellant, plus 11 metric tons of helium-3 deuterium fusion fuel. The hydrogen is heated by the fusion plasma debris to increase thrust, at a cost of reduced exhaust velocity and hence increased propellant mass. The main alternative to magnetic confinement is inertial confinement fusion, such as that proposed by Project Daedalus. A small pellet of fusion fuel would be ignited by an electron beam or a laser. To produce direct thrust, a magnetic field would form the pusher plate. In principle, the helium-3 deuterium reaction or an aneutron fusion reaction could be used to maximize the energy in charged particles and to minimize radiation. But it is highly questionable whether it is technically feasible to use these reactions. Both the detailed design studies in the 1970s, the Orion drive and Project Daedalus, used inertial confinement. In the 1980s, Lawrence Livermore National Laboratory and NASA studied an ICF-powered vehicle for interplanetary transport applications. The conical Vista spacecraft could deliver a 100-ton payload to Mars orbit and return to Earth in 130 days, or to Jupiter orbit and back in 403 days. 41 tons of deuterium, tritium fusion fuel would be required, plus 4,124 tons of hydrogen expellant. The exhaust velocity would be 157 km per second. Magnetized target fusion is a relatively new approach that combines the best features of the more widely studied magnetic confinement fusion and inertial confinement fusion approaches. Like the magnetic approach, the fusion fuel is confined at low density by magnetic fields while it is heated into a plasma. But like the inertial confinement approach, fusion is initiated by rapidly squeezing the target to dramatically increase fuel density, and thus temperature. MTF uses plasma guns, instead of powerful lasers, leading to low-cost and low-weight, compact reactors. The NASA MSFC Human Outer Planets Exploration Group has investigated a manned MTF propulsion spacecraft capable of delivering a 163,933 kg payload to Jupiter's moon Callisto using 106 to 165 metric tons of propellant in 249 to 330 days. This design would thus be considerably smaller and more fuel-efficient due to its higher exhaust velocity than the previously mentioned Discovery 2 Vista concepts. Another popular confinement concept for fusion rockets is inertial electrostatic confinement, such as in the Farnsworth-Hirsch fusor or the Polywell variation being researched by the Energy Matter Conversion Corporation. The University of Illinois has defined a 500-ton fusion ship 2 concept capable of delivering a 100,000 kg manned payload to Jupiter's moon, Europa in 210 days. Fusion Ship 2 utilizes ion rocket thrusters powered by 10 He3 IEC fusion reactors. The concept would need 300 tons of argon propellant for a one-year round trip to the Jupiter system. Dr. Robert Bussard published a series of technical articles discussing its application to spaceflight throughout the 1990s. His work was popularized by an article in the Analog Science Fiction and Fact publication, where Tom Ligon described how the fusor would make for a highly effective fusion rocket. It was also featured in this role in the science fiction novel The Wreck of the River of Stars, by Michael Flynn. A still more speculative concept is antimatter-catalyzed nuclear pulse propulsion, which would use tiny quantities of antimatter to catalyze a fission and fusion reaction, allowing much smaller fusion explosions to be created. Development projects: CMS-NW magneto-inertial fusion-driven rocket.